Okay. Well, for people who are joining this live stream, this is a continuing discussion about quantum computing capabilities for Wolfram Language. And we have a preliminary implementation of lots of things here. And I guess we're about to look at them. So should we start off with quantum discrete state?
Yeah.
So does this have examples and things as well?
Yes, for that one.
Oh boy. Okay. So, okay, so what about a more sophisticated version of this? Let's see. So what is this thing? That is funky.
Yeah, so we had talked about ways to represent the quantum states graphically, and in order to encode the phase and amplitude information, this was the simplest way that we could come up with.
Okay. Well, I think that's a separate. Why is there so unbelievably much space around the around that?
So
block
that's
space?
something that I was just prototyping, and we could have I could take another look at it, or
okay, all right, okay, fine. But let's not obsess about that yet.
Right.
Okay. So, boy, there's a lot of stuff here. Okay.
Right.
So where should I start looking to start seeing a more complete example? Is quantum circuit the place to go?
Quantum circuit and quantum operation will have some other things.
But then the documentation here looks rather incomplete. Oh, I see it. It doesn't have anything for these other ones either. Okay. So, okay, let's look at your quantum discrete state first of all. So what you've got, that's quantum object arrow values, is that right? So that's wire one arrow and then what it is.
Yep.
Is that the concept?
Mm-hmm. And we implemented the summary box for each thing. So now you can get different, you can extract properties about the quantum state.
Right.
I have a little bit of philosophical issue here. The state is the state. The state doesn't assume values.
Right. So that's one thing. Potentially, we might want to call this quantum discrete system, and then that system takes on states.
Okay.
I don't understand what you mean, Michael.
Okay, so the quantum discrete state, I think it doesn't yield anything. It represents something. And the state is the state. There's not more to be said. It's the end of the story. Like, so
as opposed to what?
As opposed to what is written here, that things assume values in the state.
So this is some sort of state expressed in some basis of states.
I know, but this is not what it currently says.
Okay, well, hold on a second. So there are a bunch of objects, 3 wires or something. And these are assumed to be, those are assumed to be some kind of outer product of things. Is that right? I mean, wire 1, wire 2, wire 3 are all intended to be independent. In this case here, these are independent quantum objects. Is that true or not?
So yeah, when you write them separately like that, then they're assumed to be independent quantum objects, and the Kronecker product is taken. But then in the second example, you have
it's a product state.
Mm-hmm. The second example is something have a something where they're not just product. You could have entangled quantum objects.
Right. So this case, you mean this case here?
Right.
Where those are the quantum objects and the values somehow represent some entangled thing.
Exactly.
And I don't understand what this is now here.
So the product is if you'd already generated quantum states, and there's examples of all these things below.
Okay.
But if you already generated quantum states, for like wire 1, you had one quantum state, and wire 2, you had a different one. You could just you could use that constructor to take to make the product state.
I'm confused here. What? So wait a minute. Why is there okay, this trace thing here, I don't understand this, because what we've got here is a case in which we've got quantum object goes to values, And now we've got this thing, product, for example, which is sort of standing in the place of a quantum object, but it's not a quantum object. What is it?
So this is what so we could represent this as an external product of previously specified quantum states. It's just that to save some symbols here for the moment, we are putting this inside. But you can see this as a quantum state product. And then
so there's also an option to, if you want to be consistent about the notation, you can do quantum state, a discrete state of, and then in the first are like product or mixture or trace, you could say quantum objects, then arrow, and then you can have the stuff that you had in as the input in the first and second examples. So that's just another constructor. But if you don't put a constructor, then it assumes that it's just quantum objects.
I didn't quite understand that. I mean, but let me just try to get a sense here of what the right-hand side, what the values here can be. So what does this mean? That
means that you are taking some system wire 1, which is a qubit, and you're putting it in the 0 computational basis state.
Okay, so but we've got several different things running around here. So this is, what the heck is this now? So this is saying we've got 3 quantum objects,
all of which are assumed to be qubits unless otherwise specified. Okay. And they're put in the register in the computational basis 4 state of this, 0 through 7.
Okay, so let's see, and so that word, like basis state, would just be represented by some state vector here. Is that the idea? Which in this case, I don't quite understand this.
So the basis state, the difference there is if you were to have 2 wires, so if you had wire 1, wire 2 goes to basis state, then and you put in, it would be after the 0, you would put in another 0 or a 1. And so you're basically specifying the basis for each of the wires individually, whereas for register,
why is it 0, 1? Why is that the right representation? So if I said here sort of W1 comma W2, right, goes to basis state 0, 0, is that right?
Yep.
Okay, now explain this to me. This is, why is it 0? Oh, I see. That's because it's thought of as a qubit, and qubits have value 0 or 1.
Right, exactly. We're working in this canonical computational basis where you have 0, 1 next to it.
What happens if I use true and false instead? Do we accept those?
I can easily change it so that we do accept those as well.
Seems useful. I mean, okay. So now that there is, these are labeled with 1, 1, 1, 0, 0, 1, 0, 0. Is that right?
So you can actually, if you just do the % sign and then say basis kets, or I think it's basis states, or something like that. Then it gives you an ordered list of what the bases are that we're using.
What on earth are those? Just see. Okay, a little bit funky. I mean, those are strings is kind of funky.
So I can,
yeah, go ahead.
Why are they not quantum states on their own?
Because we need more information. What we're specifying about quantum states has a little bit more information than just putting 0, 0 or 0, 1, because we could be working in any basis. We could be working with qubits. We don't know, what the quantum objects are that we're working with if we just specify, a 0 or a 1 like that. But this is just telling you what each entry in our state vector corresponds to in this combined basis.
Look, I think you should call it something like basis labels or something for this.
So if you put in, try basis labels right now.
Oops, I need to go %838. What does that mean?
That's saying that the first element corresponds to the basis of wire 1, and the second element in the basis states corresponds to the basis of wire 2.
Okay. Well, look, I think that getting this out is useful, but I don't think, as Michael says, it seems to me that the basis states are whatever the representation of that state 0, 0, 0, 1, etc. is. Or am I confused here?
Well, there is an issue here, which is that we are expressing vectors in terms of other vectors. So that's something that has to stop at some point. We have the same issue with vectors as lists of numbers in the Wolfram language in general. So we don't have a representation of the abstract E1 vector.
Right. But I mean, okay, right, but fine. But this is also, and by the way, the ordering here from 0, 0 to 1, 1, is that forced by something or is that arbitrary? Because, for example, our Boolean functions are ordered the other way around. So in other words, if I say something like, if I do, my favorite, something like this, whatever, I mean, let's say something like that, right? That's the way around it's ordered. So what determines this ordering in this case?
That's just the conventional ordering that's used in the quantum information community.
Yeah, I think it's outer of 0, 1, 0, 1.
Exactly.
Okay. Well, it's a little bit funky because it's the opposite way around for the way our Boolean functions work.
So we can do some thinking about that.
Let's not get stuck on that particular issue right now.
So you mean that in general we sort true before false, something like that?
That is correct.
I see.
Yeah, because that means if I label a Boolean function, if I say Boolean function of, I don't know, 7 or something, AB. Oh, great. Well, anyway, this will have, I think I can do a truth table, can't I?
Yes, I mean,
what's it called?
Yeah, Boolean table. Boolean table.
Does it do it even without? Yeah, okay. Okay. What does that mean anyway? I'm now confused by what that actually means.
Well, can you use and or something like that?
Yeah. Well, that's not going to be useful because it's commutative.
So I think that the issue here is you were doing 2 variables, right?
Yeah, I mean, you see the ordering there? I think that's the 7. That's the case. That's Boolean function of 7 is that. So in other words, if we are using a Boolean function to represent some, to convert that to some quantum function, it's going to end up the wrong way around. Okay, so Jose and I can do some thinking about that after this. Okay, fine. All right, I'm just flagging that point. Okay, but that's not the most, okay. The more important issue here is the way that you're representing, this whole product states thing and so on. And the question of whether, okay, so Michael has raised the question, is quantum discrete state the right name? And your argument, I mean, if I were to add a W4 here that was some completely unrelated thing, your argument, Michael, is what? About what?
No, my argument is that the naming discrete state is very rarely used. I think most people would call it a state of a finite dimensional quantum system. Like, there's nothing discrete about the state. The state is still continuously parameterized. It's the dimension of the embedding system that makes it discrete in this sense.
Okay, so you don't like the word discrete?
No, at least not in this usage. I don't like it. Because
you think, because it's finite dimensional, as in it's got perfectly good real numbers complex numbers in these state vectors and things, but
Exactly.
it is
finitely many basis vectors.
I mean, what is it? It's really a finite system. It's a finite quantum system. Is that right?
Yeah, so maybe we should say quantum finite system.
Well, but as opposed
what does
to
it mean for a system to be finite? What do you mean by this phrase?
I mean it isn't a field. It's got only finite and many degrees of freedom.
But harmonic oscillator is also not a field yet. It would not fall under this.
How would one represent? Okay, so what, like solutions to the Schrodinger equation? You know, with. So you're saying, okay, so what is the hierarchy here? So it's these things which have qubits and so on, which are discrete, you know, spin up, spin down type things. Then we've got things like solutions to the Schrodinger equation, if I'm not mistaken. Is that right? I mean, what's that? You know, to the spatially
continuous differential equation solution.
Yes.
Then we have infinite. Then we have infinite tensor products of these finite dimensional ones,
which are which are the quantum fields.
No, like a spin system. We have a Ising.
Yeah. Okay. Right. And
then we have infinite products of continuous systems.
Okay. Okay. And so the analogy of that with our other kinds of systems is, what is the analogy? So we've got, you know, discrete lists of, we've got lists of discrete, well, okay, so nothing here is at the lowest level discrete, except for the fact that the number of degrees of freedom is finite.
Yeah.
And the representation of what's going on is just numbers as opposed to functions. Like
no, they could be represented by functions. They could have parameters.
Yeah, okay, but they don't have spatial extent, for example.
Correct. There's no spatial variable.
So,
and if we were to extend this to include those kinds of things, what would be involved? What would it then look like? What would things start to look like then?
In a Heisenberg view, these vectors would become infinitely long.
Where, by the Heisenberg view, you mean where the state vectors are evolving as opposed to the operators? Somehow.
No, where I mean matrix mechanics versus Schrödinger's wave function.
Oh, I see. Okay, right, fine. But I see. But then, okay, but then if we look at the transition to quantum field theory, where we're looking at S matrices and so on, those is the S matrix the generalization of the thing you're describing there? I mean, it's the operator that acts on those infinite dimensional vectors. Is that right? Or am I confused?
I think there's one more step in between. So I think the first step is, here we have a finite dimensional vector space in which this all lives. The qubit lives just in C2. So then we make it infinite dimensional one to represent a function, like a harmonic oscillator function. Then we need a Fock space of infinitely many of them to represent the field. And then we have S matrix.
Okay, I understand. So, okay, so your issue here, sigh. Okay, what would this look like if we were going to have a spatially extended thing? I mean, in current quantum computing, people, I mean, like for example, in standard computation, we think we're dealing with bits, and we don't discuss any kind of spatial extent of bits. In some kind of analog computing thing, we might, but walk me through what we would do if we were generalizing this framework to deal with sort of standard Schrodinger equation type things. Like, for example, when we need to do our stuff with molecules, is there a way, what would we ultimately do to represent, the water molecule, for example?
This one I feel like has a little bit of simpler things, because we would only be interested in a position representation of the waveform, which would make it much easier. But here we want to represent in a way that we can go to any basis. Like only few people already look at the momentum distribution of a water molecule. Not to speak about any more bizarre.
Yeah. Well, so you're saying we can lock in this case, we're allowing an arbitrary basis. In the case of typical quantum chemistry, we're locking it down to some kind of position.
I think so, yeah.
But the main change, I think, would be changing from a vector-based description to a function-based description.
Yeah.
And there is no nice connection, like we don't have any way of going from our lists of numbers to our functions.
Mm-hmm.
And that's why from the beginning we have tried to restrict to what we call the discrete case, but Michael is right, the proper name is finite dimensional. It has to be the whole word. But finite finite typically means spatial.
Yeah, right. But I mean, then this becomes, in the case where we've got instead of those discrete degrees of freedom there, we instead have something which is an arbitrary position. Is that right? We have a degree of freedom there that right there is 3 degrees of freedom, each of which, or am I confused here?
Yeah, no, you're right.
Okay. So it's that left-hand side that somehow becomes more elaborate.
But a lot more elaborate. It's not just changing. I mean, we have to change that list of 3 numbers by a function.
And the point of restricting ourselves to these finite dimensional systems is that for quantum computing, that's all that's ever used.
Right, so far.
And I hate to do this again, but I think it might be wise for us to move on, and then Michael, we can again have a discussion offline.
Yep.
Okay.
Just because
the main fine.
I think the functionality is just right. No problem with just the name. Okay, I feel like is.
I'm bothered by an aspect of the functionality. Okay, so I mean, this way of just saying this is what it is and that's the state it's in is a little weird to me, and we're not even documenting that, are we?
So if you look at the other examples down further, there's a lot of other examples like that, and we didn't want to put like 100 things in the documentation. We thought the examples was the better place.
No, it's not right. You have to have it all in the documentation. It has to be all listed in the documentation. Okay.
Yeah, I think I share that feeling of right now we are packing too many things into the constructor. And my main worry is when we go symbolic, when users say, I have a state S1 and another S2, and they don't say anything about them. So these doesn't fit very well right now with this.
And how does that work? How would you construct things? And then they want a product state of those two.
Exactly. So in the same way that we have now, say, tensor product, and we have tensor product of V1 and V2, and that's fine. It's just they are waiting for users to change V1 by a list and V2 by another list, things like that. Yeah. So we may go that route, but I'm not sure how many symbols we would be forced and whether we can reuse tensor product for here.
Well, I mean, is it the case that this W1, W2, W3 is in fact alternatively described as a tensor product? No, it's only described in this case where it's a basis state. So some of them it's a tensor product, some of them it isn't, right?
Right, and that's what led us to this design in the first place.
And going back up here, this product thing, I'm now totally confused. So this is, you've got to write out what the possible forms of vowels actually is in the details there.
Okay.
And okay, so this is a phi plus state, whatever that might mean.
That's one of the Bell states. So it's an entangled state.
Okay, fine. What's this?
That's one of the things in the documentation above, where it basically says you take a quantum state that you've defined and you're tracing out a subsystem to give you a smaller quantum state.
Yeah, I looked at this one earlier. I think it's nice functionality, definitely needed, but I would rather come from the outside operating on it.
So we also have a function. We didn't know whether we would want it or not, whether we want to use it like this or in the regular function, but it's called quantum partial trace or quantum partial TR, and it performs that functionality. So you don't actually need to do it internally like that. We just have both options at the moment for whichever one was preferred.
Well, so these are quantum operations. These are quantum state operations or something, as opposed to whatever this is. These things like product and so on, you could imagine having them on the outside where these things are called something like, I mean, maybe I'm wrong about this, quantum state operation. I mean, if we wanted to save on product, and then that in turn, you know, something like this. Is that crazy?
Okay. I can.
Michael, what do you think about that?
I think it seems fine to me.
Okay. So that gets us out of this weird situation here.
Okay. So that's easy to do. I can do that, no problem.
Okay. All right. Let's keep looking at some more of these things here. So then I get it. Those are, by the way, there's something wrong with this formatting. This formatting is really weird looking.
And this is just formatting that I came up with on my own. I don't have the background in design. So,
but I'm just, I guess what I'm saying is, when we represent a quantum discrete state, what do we want to know? I mean, this isn't the object's kind of the left-hand side thing, because it's the left-hand side thing in the definition of the quantum discrete state. And then
that's
the right-hand...
the name of the object. That's not the state of the object. You have an electron named E1 that isn't the state.
Okay, but that's...
You can also expand it and see what other things we have.
Okay, but in an alternative name here of quantum finite system, for example, let's imagine that this was called quantum finite system.
No, I don't think so. That's a bad name, because we don't represent a system. We represent a state we believe a system is in.
No, but there are systems that behave quantum mechanically, and those take a state in some Hilbert space.
But we don't. But we don't have the level of representing the system symbolically.
Yeah, I agree with Michael. Here we have to describe the states of a system. The system is a lot more abstract.
Okay, so what? Okay, so we've got quantum discrete state, quantum finite state, whatever the heck that means. I don't know. I mean, you're saying the full correct name is quantum finite dimensional what?
Finite dimensional quantum state would be my preferred one. I know it's a little bit long.
Finite dimensional quantum state. Well, it would be really nice to start with the word quantum finite dimensional state. We have a couple of suggestions here from the live stream. Somebody just suggesting quantum state. I think that's, and things like list quantum state. I think that's going to get super confusing. Quantum state cells. Can't you have a standard construction and specify an alternative basis by optionally saying basis, arrow, whatever? A finite system would be a quantum cell. I've not heard of quantum cells. Anybody here heard of quantum cells?
No, never heard of it.
Yeah, that is in Wigner phase space representations.
I see, but which we're not doing here. This is not. I mean, that's in the world of position.
Not yes and no. While we don't have finite dimensional realizations of the canonical commutation relations, with Schwinger's construction, we have the nearest one we can get. So we can build the nearest equivalence of Wigner's for finite dimensional system.
Okay. Somebody is suggesting the word construct. Always a word which is ambiguous. Yes, it is. It is multiply ambiguous, not least because you can either read it as construct or construct, and it kind of, I think, goes downhill from there. But look, okay. So what you're saying is quantum finite dimensional state is then what would you propose for the quantum discrete operation thing?
I would actually say this one can be a quantum operation, because whatever we say, what is the concrete operation, would make it clear when it acts on a quantum state, if it acts in a discrete or continuous fashion.
Okay.
There might be no need to differentiate explicit between the discrete and the other version.
All right. Well, let's keep going here with this rather ponderous quantum finite dimensional state.
So I like the quantum state operation, product, trace, all of that stuff. What you suggested. I think if we want to look at quantum discrete operation and then actually quantum measurement distribution, I think those might be useful, because I tried to implement a lot of the stuff that you had mentioned previously.
Okay, let's take a look. Okay.
So here, instead of before where I had quantum discrete operations and I just had the unitary ones, and then we had different symbols for observables and POVMs and all of these things, I took your advice and tried to put it all in one format, and you can just specify the type of operation you want.
Okay. So
then this way, you're everything is just some quantum discrete operation, and your circuit just consists of a bunch of quantum discrete operations, not discrete operations and observables and POVMs and other things.
Let me take a look at what some of these are. Okay, quantum discrete operation, unitary. And the W is what this is acting on?
Yep.
It's a little funky that you have to put what it's acting on so deep inside the operation itself. I mean, it would be like having to say, this squaring, this function is specifically operating on this element of an association. That seems unfortunate that you have to say what it's operating on inside it here.
Right. So that's one thing. One of the two things that I wanted to talk about today is a functional representation. Essentially, what you're saying right now, where you don't have to specify when you create the operation.
Yep.
And I have some ideas for that, but I want to formalize them first.
Well, let's okay. All right, fine. So that seems wrong to me. This should be a pure function thing without saying what it's applying itself to. Sure. And these operations don't, if I'm not mistaken, they are applying themselves to, well, how many degrees of freedom could be in here? Could there be multiple degrees of freedom that are in the same, that this operation is essentially a two-legged operation that's applied to 2 degrees of freedom, or just always to 1? It can be 2, right?
So you can have as many as you want, actually. The already created gates that are like internal in this package are go up to having 3 qubits.
Okay, fine. So a typical controlled NOT gate or something.
Right.
I don't understand why it isn't a functional representation already. I mean, in other words.
Yep. That's something that was on the list. That's something that will get done.
Okay, but hold on. So this here, okay, so the condition here would surely be in most cases a pure function that applies to I'm completely confused why I mean, it seems to me that this form here should be instead let's say it's quantum operation unitary arrow controlled NOT or something. And then that simply acts on this. Is that right?
So one of the problems that we had with that is because the operation itself has properties that we wanted to be able to extract, and we thought it was it wouldn't really work to be able to be having the brackets, the quantum object, and also bracket the property.
Ugh. And also the other problem is that this is ultimately going to be applied to a quantum finite dimensional state.
Exactly. And so that's why we decided on this type of representation. But I had some ideas for how to do it functionally.
What are your ideas?
They're on the other computer, unfortunately, because
the lost computer. But are they also in your brain, or can you say something about them?
I can email them to you guys after. I don't want to waste our time trying to reconstruct it.
So can we use W in the second argument here, like acting on this state comma W, like when we say do something on this polynomial comma X?
Yeah, I understand. That makes quite a bit of sense. But what we're then missing is the ability to extract properties from this quantum operation, and that's why, in some cases, that's why we end up with things like classifier information and so on, rather than because the classifier itself is acting on actual data. So, what kinds of properties of the quantum operation, which sadly are not documented here, but what kind of operations?
So there are examples. You can go down and you can get out the matrix representation, the inputs, the like the qubit dimension, things like that.
Okay. Humph. Well, I mean, we actually have this general information function. I mean, sadly, it's sort of a pun relative to quantum information, but forget that.
We could call it data or value. We have examples of other cases.
Yes. But I mean, it's an extractor function that extracts essentially information from this, from the operator here. And then, yeah, I mean, I think this is an interesting idea to think of these things like they are markers in the same way that X and Y in a polynomial are kind of markers. The polynomial could be turned into a pure anonymous function, but in fact, you're using X and Y to indicate where certain, data goes. And you could argue that the same thing is what's going on here. Is that a fair argument?
Yeah, I like this construction.
I think so.
I think that this is good. And I'm glad that we were able to get to this point.
Okay, let's look at quantum finite dimensional state and how that relates to this as well. Because what that's saying is, see there, what is the analog? I mean, if this is our polynomial, okay, and this is saying where in the polynomial to go looking, this thing here is a little...
Instead of naming like W1, we would just put like, #1 or something there.
An even better analogy might be a tensor and its indices, because it's discrete. And I think these W's are acting like indices, actually.
I'm sorry. So you're saying it's like an association, like having an association here or something?
Not so much an association, but the indices of a tensor, like when you say it's matrix ij. So this is like I, j, and j.
Which is then what? Like a sparse array type thing?
No. So we can describe these indices positionally, like the first index or the second index, or we can give them names. And then things like transpositions, it's just exchange I and j and things like that. So I think this is more like this use of indices in tensors.
Okay, but then what are you proposing, that there be a mechanism, that one mechanism here would be that this could be a pure list of values? That this could be so that the effective default name of the first degree of freedom is just 1, that we could have something like this. That's a thing with 1 degree of freedom whose name is 1.
But how, in general, would you be able to specify? Okay, one of the arguments that I had before is the option, or I guess it's an option in the quantum finite dimensional state, is qubit dimension, which allows you to basically from the qubit dimension, you would be able to infer, given what you just put and things of that nature, how many slots you have.
What do you mean by how many slots? I mean, look, if I had...
So if you just put in a numerical array, then, and your numerical array had 4, was a list that had 4.
I see. Then it's a 2, and the qubit dimension is 2, then you're saying that implies that is just the unrolling of a 2x2 thing.
Right, exactly. Whereas
the very fact that it's unrolled is kind of unfortunate, but I mean, certainly it's a convention in this business.
And we have to do some unrolling in order to be able to differentiate between states of higher dimensions or just entangled states that have multiple quantum objects inside of them.
Yes. And also, if we're going to use any kind of matrix formalism, we better have unraveled like that. Otherwise, we're not using matrices. We're using some kind of higher dimensional tensor, if I'm not mistaken. In other words, if you want to make if the quantum operation is going to be represented by a matrix, you've got to unroll like that. Is it completely obvious that one should be representing it by a vector, and that isn't just some convenience for hand calculation or some weird thing like that?
I think it makes sense to do it this way. So Jose and I have thought about this a fair amount, and I mean, we can go back to the drawing board and look at it again.
Well, I mean, but let me just understand it. So the formalism of quantum mechanics is in terms of matrices, has been for 100 years.
Right.
The question here is, if you've got a direct product, the outer product state, let's say it's a collection of 3 standard binary qubits. Okay. Then one way to represent that would be as a rank 3 tensor, if I'm not mistaken.
Right.
Okay. But now operating on that rank 3 tensor, you would then end up with, for us right now, let's imagine that you had I don't know how many, let's say a controlled NOT gate has 2 inputs. So let's say like a Toffoli gate or something has 3 probably.
Yeah, Toffoli, Deutsch, Fredkin, any of those.
All my friends all have 3 input gates. How nice. Okay, so so imagine a Toffoli gate, for example. Okay, and it's acting on this rank 3 tensor. What is then the form of that gate? What does that gate? I mean, normally it would be acting on the unraveled, 1 1 1 1 going down to 0 0 0, or the other way around, length 8 vector, right? It will be an 8x8 matrix acting on a length 8 vector, if I'm not mistaken.
Correct. Right? Whereas in the other sense, it would be, as you're saying, a rank 3 tensor acting on the other.
No, it isn't a rank 3 tensor. It's a rank 3 tensor is the thing it's acting on.
So it's a rank 6 tensor then.
Is it? Yeah. Is it a rank 6 tensor that returns another rank 3 tensor?
Yeah.
Okay. Is that obviously completely stupid? I mean, what form does it have as a rank 6 tensor? Is it nice? And if you were to take that rank 6 tensor, is the natural rank 6 tensor related by array flatten to the rank 2 8x8 matrix?
It's related by flattening and transpositions, but it's just more difficult for the user to have to input something like that.
I'm not completely convinced.
So this happens also with tensor product and Kronecker product. It's basically two different communities that are more used to only matrices or tensors of arbitrary rank.
Explain that. I mean, so
yes. So we get frequently comments from people saying, "Oh, why am I doing this tensor product? Am I getting something so deep when I want just a matrix?" And the answer is always the same. You shouldn't use tensor product. Use Kronecker product, and then everybody's happy.
But
because some people
tensor product followed by array flatten.
Yes, it is. But some people are feel very uncomfortable using higher depths.
Yes, I understand that. But the advantage here is that if one did it that way, I mean, maybe I'm not thinking about this correctly, but isn't it the case then that, right now we have integer indices, but we could imagine having at every level, having, for example, I see. I mean, this is,
I think
it's a curried function. If in the case where it's a function of three, if we were looking at sort of Schrodinger equation stuff, we would end up with some weird curried function of three-level curried function to represent the positions of three particles. Go ahead, Michael.
I think it's the same what Jose just said. It depends on the community. In the quantum computing area, people like it just as a vector. But people who deal with spin systems, they definitely prefer the tensor product.
Lovely. Okay.
So unfortunately, I only have another 10 minutes before I have to TA.
Okay. And we have another meeting also here. I think we should wrap for right now.
Do you want to just very, very quickly look at the quantum measurement distribution? That'll take just a minute.
Other types of operations, like Boolean functions. Well, I just described an issue with Boolean functions because of this.
Right. There's another issue with Boolean functions in that, in general, Boolean functions are not invertible. Whereas in quantum, I wanted to.
It's very hard. The very small fraction of Boolean functions are invertible.
Right, and so I wanted to see.
I've looked for the ones that are, but there aren't very many.
Right, and so it was one of the questions was whether we want to restrict ourselves to invertible because those are the only ones that are by themselves quantum friendly, or we want to allow all binary Boolean functions and then convert them into quantum acceptable.
I don't know how you would do that.
Well, there's a way to convert them into quantum circuits that are just a bunch of unitary operations and then measurements. But it gets very messy.
What about? I mean, if you apply, I'm a little confused here. If you take a pure state and you apply one of these information destroying functions to it, don't you get a mixed state?
So what would be an example of that? Like what's
tracing things out?
What's that?
Tracing things out.
Yeah. I mean, don't you, if you take two qubits and you AND them, not any kind of controlled, quantum AND, you just AND them the ordinary way. I believe that you simply get a mixed state out.
And it's not a well-defined quantum operation, but what you can do is you can perform a controlled knot operation on some extra wire, which is we call an ancilla, and then you reverse all the intermediate computation steps so that it's as if you had an AND gate at the end.
Am I simply wrong that you get a mixed state out from the thing I described?
Yes, because everything is unitary.
Okay.
There's just no way around it.
But you
so the operation, so you can't represent the non-unitary operation is your point, Michael.
There isn't a non-unitary operation.
Right, but you can implement things like the AND gate, the analog of that in quantum, by using some combination of unitary operations and measurements.
I see. But so, and then what would you get out? You would get out something in the classical limit, or is there a classical? Is there a classical analog, or is there no classical analog?
I don't think there's a classical analog here.
So what is the relationship between the quantum, the puffed out, quantum and the non-quantum and?
So the quantum and is just the circuit completely reversible up until measurement. That's the only difference. So it's just decomposed. It's just a matrix decomposition, essentially.
Okay, let's look at this last thing here, and then we've all got to go for this meeting. So what is this now?
So you had suggested that instead of just having measurements, we keep everything in terms of some more symbolic distribution, and then you can perform all of the general distribution.
That's cool. That's seriously cool. Does it work?
Yep.
So in other words, what you're saying is that, yeah, this is cool. This is a packaging. So the thing you should show, okay, what about things like the Cauchy-Specker theorem and things like, can't you represent, given that you have this distribution, can't you represent all those kinds of funky combinations of measurements and things that way?
The what? What was the thing?
Cauchy-Specker. It's one of the, it's a sort of, it's a fancier thing than Bell's inequality.
No, it's a proof of contextuality.
Okay, I have to look that up. I'm not familiar with it.
Okay, but I mean,
it's not enough to measure an operator. You always need, for every proper measurement, a complete set of commuting operators so that all degenerate eigenspaces are totally resolved.
Okay, but my question is, in terms of this representation, can I get to see all of that in a cool way using this quantum measurement distribution, or is that the wrong direction? Shouldn't I be able to see all these various Bell's inequality-ish things from this quantum measurement distribution?
I think so.
No, I don't think so. Because like Bell is not represented in the distribution.
No, I understand that.
It's represented in the correlation between individual results.
No, I understand that. But what I'm saying is that this distribution is, this is the classical version. And then the whole point would be, well, let's see, that you should still be able to get a joint distribution out. Now I'm getting myself very confused because I know that you can't get a joint distribution out because that's the whole point of Bell's inequality.
You can still form expectation values.
Yes, you can. But and this is and so this is the expectation value. Is that right? But then you're taking the expectation value of this again. I'm confused. All right. Unfortunately, we have to wrap for right now. We clearly have quite a bit more. I think we have at least 2 more hours of going over this to do.
But we're making progress.
Yes, but I think it'd be useful to get in the documentation here to really list out all those different cases and possible things up there in that documentation. I think it would also be useful to start getting together a guide page that lists all these various functions.
Okay.
And I don't know what a super operator is here.
That's like, basically you can operate on your quantum state from both sides, like left and right, matrix multiplications. It's like a quantum channel.
Okay. So I have another question here. We have had an increasing number of contacts from the people who say they have quantum computers and are offering various kinds of APIs and so on. So I think it would be worthwhile after we do 1 or 2 more iterations on this to get a meeting with either sequentially with several of those groups or together with all of those groups to go over what we what we're doing here.
That sounds wonderful.
Okay, well, we have to, I guess partnerships has to communicate with these guys. Maybe we should try doing a couple of them separately before we do a big one with everybody together, or we'll end up with some kind of, we'll end up with having to explain basic things to a large collection of people, which will be annoying. All right, okay, so are we going to be able to follow up, like, let's say this week on more, let's do the next iteration of this if we can this week. Okay, anything else?
I think that's it.
Okay, thanks a lot. See you later.
Thank you.
Bye.
Bye.